Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 76th Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 76 is counting summations. It is possible to write 5 as a sum in exactly 6 different ways. How many different ways can 100 be written as a sum of at least 2 positive integers? Okay. So, the hard part here is the mathematics, which I've already done a lot of thinking on. And I think that the correct approach for this exact problem is going to be recursion. So, I'm going to copy down some notes I have here. Okay, so if we imagine a function that takes in an n, and that function tells us how many different ways n can be written as a sum of at least 2 positive integers, then f of n is the sum of the series f of n1. So we're also going to have this function f in x, where x is less than n, and this function is the number of ways n can be represented as the sum of integers starting with x. The wording's a little bit confusing here, but basically what I mean is like f of 8, 3 would be counting things like 3 plus 1 plus 1 plus 1 plus 1. 5 ones there. But not anything with the number 4. And not anything that does not contain a 3. So if we think of these lists, and let me just pull down the list for, let's do for 6. Or let's say for 6, the different ways of representing 6 could be like 6 ones, and then a 2 and 4 ones, 2 twos and 2 ones, 3 twos, etc., etc. Okay, so if n is 6, then f of n1 is how many start with 1, which happens to always be 1. You can only represent it with only ones in one way. And then for 2, these 3 start with the number 2. And then these 3 start with the number 3. These 2 start with the number 4. And this last one starts with the number 5, and that's the whole thing. So just thinking through the mathematics of this problem. For now, sorry, I've got a whole bunch of notes. So f of 1 is always 0, f of 2 is 1, and we can do a few more there, but, like, it's not super necessary. So let's see. F of n1 also always equals 1 because there's only ever one way to represent an integer as a sum of ones. F of n2 is always equal to the floor of n divided by 2. So for 6, there are 3 ways to represent it as a sum starting with the number 2. For 5, there are 2 ways, as we can see in our example here. And then for 10, there would be 5 ways, and so on. And then what we can say is f of nx, outside of a couple of special cases like that, generally speaking, well, there's a few different equations here. And I'm going to copy all of these down. Okay, so f of n of x, where x is less than n minus divided by 2, is the summation of f of n minus x 1. So this is where you can start to see where I'm thinking recursion. And then we have this special case where f of n in minus 1 is always 1. And that's actually, you can go a little bit above and below that. But anyway, let's go ahead and start writing code, and then maybe the math will be a little bit more clear for people who aren't already huge math nerds. So we're going to define, let's call our first function is going to be count sums largest. So this is going to be this f in x part. And here there's a few specific return cases, such as like if x greater than or equal to n, I'm going to have it return 0. I'm hoping to program this such that that is never a thing. Okay, I don't actually like one-lining things. If x is equal to n minus 1, return 1. Otherwise, I'm going to say if x is less than n divided by 2, then I am going to have to do a sum equals 0. And then for I in range 1 to x plus 1 so that it is inclusive, sum plus equals same function, n minus x, I. And then if x plus 1 is equal I'm probably going to want to do this one first. But if x plus 1 is equal to n minus x, then I want to call count sums with n minus x. I'm not 100% sure how well I can do this, since both of these functions are going to need to call each other. But let's just go with this. And then otherwise, return. It's going to be this plus 1. Now. Okay, so I think if I just do int of n divided by 2, it'll work. Making sure I get that edge case there. Let's see. So I'm going to do 1, 2, and 3. Okay. I could obviously go do more there. I could do less there. And actually, I'm just noticing now that I could say if n less than or equal to 3, return n minus 1. That does stop being true at, like, n equals 4, I think. So otherwise, we do a similar pattern to what we did here. For I in range 1 to n. And this time, we don't actually want to go up to n. And then we do sum plus equals. And then we return sum. Now, I'm not 100% certain that I have coded this completely correctly. We're gonna have to find that out together here. But let's see what it does if I say print count sums of 5. So if this works properly, it should print out the number 6. Because that was the given in our problem, was that there are 6 different ways to do 5, right? Yes. Okay, so we got 6. Let's spot check, like, a couple of others. So, for instance, because I've done all of the everything here, I know that 11 should return 55. And it does. Okay, let's go ahead and pop in 100 and see if we get the correct answer. Obviously, it's going to take a little bit longer with 100. I'm not sure whether it will go within our 1-minute time limit. Looking like maybe not. I think it is also possible to get caught in an infinite loop here, but I'm not sure. Let's give that another minute. Okay. Looking like it won't go all the way through. I'm going to pull this out into a variable just so that I can print it. I'm going to say found count of count for in this case. Okay. So it does seem to be doing the same things over and over and over and over and over and over. So something is caught in an infinite loop somewhere. Let's do 20, just to see if that also has the same issue. Okay, it does not look like it. I'm gonna go back to 11 just to, like, be able to see all my output here. Okay, it looks like things are working fine for smaller numbers. Maybe it only looks like it isn't working for the larger ones. Okay. I'm gonna comment that one out for right now. Go back to 100, even though we know that it'll... Lots of calling it with one. Let's run this and then stop it immediately. Still not immediately enough, I bet. Okay. Let's see. Maybe I'm wrong about it being pulled into an infinite loop and it's just taking some time because that's the nature of the recursion problem. And I think I should have an if x equals 1, return 1 here. Let's see if that changes the things. Okay, so that gave us a number, and it gave us a number within our time limit. So that was what I was missing, I think. Um, but of course, the proof is in, can we in fact, did we in fact get the correct answer? So let's see, and it is. Okay, so again, difficulty here was just the maths, and then a little bit of a mistake in implementing the maths. But all in all, once we figured out the I'm gonna put this back to not a variable. Once we figure out the formula, this problem is relatively easy to implement. But of course, it is also relatively easy to make a mistake because there's a lot of little bitty parts and conditions here. So I'm gonna go ahead and call it there for that one. And as always, if you would like to hire me for help with whatever code challenge you are working on, check the link in the description, and I'll catch you in the next one.